this lecture I am going to talk about population dynamics, and I will talk about a very well known model called a predator prey model. This is a very simple example of a nonlinear differential equation, and it is an extremely powerful model that has been applied not only to populations of real species, like it can be the population of foxes and rabbits, or shark and small fish, or some predator and some prey. Okay. But it's also something that is used in modeling certain chemical reactions. Okay. So we'll start with this. Let me these models are referred to as either predator prey models, or they are often referred to as Lotka-Volterra model. Okay. And I'll just write the differential equation. So the idea is that there is some prey whose population at any time is given by x, okay, and x is a function of time. Okay, x of t is population at time t, and there is a predator which is y at t. This is the population at time t. Okay, so you have a predator and a prey. For example, as I said, this can be maybe a rabbit, and this can be a fox. Okay. Now, the differential equation, okay, for the change of population of the predator, okay, is I'll write the differential equation, and then I'll tell you what the idea is. Ax minus bxy. Okay. Now, this A is the, I will call it the net birth rate. So if there was no predator, if y was equal to 0, okay, then the predator population would grow at some rate A. Okay, that is the net birth rate. So, it is actually the difference of birth and death rate. Now, this term is a term. So, x times y, x is the population of x times the population of y. Okay, this is the rate at which x and y encounter each other. So, and in an encounter, okay, obviously the prey will get eaten. So, the population of prey will get reduced due to the encounter. So this is the encounter term. Okay. So during the encounter between the prey and predator, the population will decrease, and so there is its population goes down. Okay. Now this is a nonlinear term. Okay, it depends on both x and y. Now we should also have a differential equation for y. So, y dot. Okay. Now, what we will assume is that I'll write it as minus c y plus d times x y. Okay. So this is the net birth rate, and the predator, if there is no prey, okay, the predator its population will decrease. Okay. So, if x equal to 0, then y will go to 0. Okay. So therefore, it has a negative net birth rate, but if there is predator, okay, then its population will increase, and this is the nonlinear term. So due to encounter, the population of the predator increases, okay, due to this factor d. Now these are again so these are set of coupled nonlinear differential equations. Now, let us look at the critical points. So if I put x dot equal to 0, that implies a x equal to b x y. Okay, that implies x equal to 0, or if x is not equal to 0, y equal to if x is not equal to 0, then y is equal to a by b. okay. And the other term, if I put y dot equal to 0, so this implies C y equal to d x y, okay. This implies y equal to 0 or x equal to c by d, okay. So basically you can see that if x equal to 0 in this case, then y has to be 0, okay. Similarly, if y equal to 0, then x has to be 0. So the critical points are basically given by x equal to y equal to 0, that is the first critical point. And in the second critical point, if y equal to a by b, so if I substitute y equal to a by b in this case, okay, then you can see if y equal to a by b, that means y is not equal to 0. So x has to be c by d. So the other critical point is given by x equal to c by d, y equal to a by b, okay. So we have two critical points, okay. And so the two critical points are 0 0, we will write it in this form 0 0 and c by d, a by b, okay. Now the critical point at 0 0, okay, this critical point, okay, is not very interesting, okay. So this is not very interesting, okay. This can only be reached, why is it, why did I say it is not very interesting, okay. So this can only be reached if x equal to 0 at t equal to 0, okay. So then what happens if x equal to 0 at t equal to 0, then what happens is y dot equal to minus c y, okay, and y will exponentially decay to 0, okay. If any other case, you cannot reach that critical point, okay. So if x is not equal to 0 at t equal to 0, then you cannot reach that case, and so this is not very interesting. So let us look at the other critical point. So let us look at C D A B, this critical point, okay. So now let us linearize equations about this critical point, okay. So what we are going to do is to take our equations for x and y and linearize about this critical point, okay. Now how will you write x y, okay. So when you linearize about the critical point, then you have a term that looks like so you write x approximately equal to c by d plus let me call it u, and y, or y equal to a by b plus v, okay. So if you think of it in this way, then I can write the first equation, okay. So x dot is same as u dot, okay. So I can write u dot equal to, so now the first term, okay, I can write a times x, I can write as a times u. So a times c by d plus u plus, now what you have is d times or b time or minus b times c by d plus u a by b plus v, okay. Now what you can write this whole thing in the following way, okay. So what you will get if you expand this out, so let us do this. So this is a c by d plus a u, let us multiply this out. So you will have b times, okay, c by d into a by b, okay. So it is so the b will cancel, so we will get a c by d then the next term you will have C by D into V. Okay. So, I will write it as minus B C by D V. Then you will have a term that looks like U into A by B. So, U into A by B into B is minus A U, and you have a term minus B U V. Okay. So, this is a nonlinear term. Okay. So, this is thrown away. So, this is a nonlinear term, this is nonlinear, okay, since it involves both U and V. Okay. It involves a product of U and V. Okay. And what you can also see is that the A U term will cancel, okay, A C by D will cancel. Okay. So, finally, what you get is U dot is equal to minus B C by D into V. Okay. Similarly, you can show that V dot is equal to A D by B into U. So, now the linear equations look like U dot V dot is equal to 0 minus B C by D, A D by B, 0 U V. So, what does this mean? So, if you calculate eigenvalues, okay, you can easily see that lambda square is equal to minus. So, the B will cancel, the D will cancel. So, you will get minus A C. So, implies lambda is equal to I plus minus I square root of A C. Okay. So, this is this critical point is stable and it is a center. And if you look at trajectories, okay, so what will happen is that if you put certain values of A, B and C, okay, then you will find that the trajectories, okay, so if you look at y versus x, okay, and we are only interested in the case where x and y is greater than 0, okay, and this point which we took, this critical point which was given by C by D, A by B. So, this is critical point is C by D, A by B. Okay. So, what happens? So, around this critical point your trajectories will be basically some sort of curves around this. Okay. So, there will be some sort of curves. Okay. We do not know what exactly the shapes of the curves are, but your trajectories will be some sort of curves around this. Okay, and remember they cannot go they cannot cross 0. So, x and y are strictly greater than 0. Okay. So, this is one case, okay, and in this case your critical point is a center. Okay. So, the critical point is stable or a center. Now, there is a small point that we have to emphasize. Okay. So, this critical point is a stable center. This is for the linearized system. For linearized system. Okay. Now, however, this may not be true for the nonlinear system. Okay, this is a very subtle part that the nature of the critical point. Okay, what we said, if we go back to what we discussed in the last class, we discussed the type of critical points. Okay, this is a type of critical point. This is only for linear system. This is for the linearized system. Okay. However, now for the nonlinear system, okay, then what is the nature of critical points? Okay. I won't go into this in too much detail. Okay. I'll just mention. Okay. So, for nonlinear system, okay, then the nature of critical point, okay, for nonlinear equation, okay, you can still linearize. Okay. So, we linearize and find eigenvalues of linear system. So, you can only find eigenvalues of the linear system, because only in the linear system you have the matrix. Okay. Now, if lambda 1 equal to lambda 2 and it is real, okay, lambda 1 equal to lambda 2 and it is real, okay, then the critical point of the nonlinear system is either node or a spiral point. Okay. So, for the nonlinear system, okay, it's either node, this is for nonlinear system. The next thing is, if lambda 1 lambda 2 are purely imaginary. Okay. So, if they are purely imaginary, then the critical point is either a center or a spiral point. Okay. So, for the linear case, critical point was purely a center, but for the nonlinear case, okay, if these two eigenvalues are purely imaginary, then it can be either a center or a spiral point. And the third case is, so all other cases critical points for nonlinear system are same as those for linear system. Okay. So, what that means, coming back to what we discussed here. So, for the linear system, this critical point, okay, this critical point that we saw where x was equal to c by d and y was equal to a by b, that is a center and it is stable. Okay. But for the nonlinear system, okay, it may be a center or a spiral point. Okay. So, what that means is that your point c by d, a by b, okay, eigenvalues are purely imaginary, okay, may be a center or spiral point. Okay. So, it may be either a center or a spiral point. Okay. And actually both these cases are fairly interesting. Okay. So, what we can do is suppose we take this equation. So, in this particular case, so it may be either a center or a spiral point. Okay, this c by d, a by b. So, if it is a spiral point, then again, based on certain conditions, you will get either stable or unstable, but this is definitely a possibility. Okay. So, what happens to the species as time evolves? Okay. Now in this particular case, where we had x dot is equal to a x minus b x y and y dot is equal to minus c y plus d x y. Okay. We can do we can divide them, okay, and we can and we can write dx by dy is equal to ax minus bxy divided by cy minus dxy. Okay. And this you can use our usual method of you can do the usual method of solving first order differential equations, like using integrating factor. Okay. You can convert this to an exact differential and then use the integrating factor to get the solution. Okay. So, the solution of this is given by a ln y minus b y plus c ln x minus dx equal to constant. Okay, you can easily verify that this satisfies this equation. Okay. So, now you can think of these. Okay, this is constant. So, for various values of constant, if you plot this, you will get a families of curves. Okay. Now, we said that a, b, c, d are all greater than equal to 0. Okay. And you can analyze this behavior for various values of a, b, c and d. Okay. You can get basically you can plot let us say suppose I plot versus time. Okay. Now you could have let us say starting from some, if you start at some point. Okay, you might have one species go like this. This might be x of t. So what is happening is that initially the population is small. Okay, and then it keeps increasing. Okay, now let me draw the curve in black also, just to show what. So this is x of t. Now let me draw y of t. So y of t will look something like this. And so on, and it will keep going. So this is y of t. Okay. So what is happening here is that initially the population of y is very low, x grows at a much faster rate. Okay, and since x is also small, okay, y is just increasing very slowly. So y is increasing very slowly. Okay, then once x becomes large enough, then y starts increasing very rapidly, because y is because of the d term. Okay, and what happens is when x is maximum, then y is really growing at a fast rate. Okay, and that causes x to go down, because this because y becomes large, this term minus bxy becomes substantial. Okay, so that causes x to go down. Okay, this causes reduction in x. Okay, but now as x goes down, the d term is also going down. So at one point after that, the population of y starts decreasing. Okay, because d becomes smaller, then y starts going down. Okay, now y goes down, it keeps going down. Okay, because x is also going down, y is also going down in this range, and then once y becomes very low, then x starts increasing, because the bxy term is small, axy term is greater. X starts increasing, and then it goes in this sort of periodic cycles. Okay, so what you have is that the population of each of the species shows oscillatory behavior. So oscillatory behavior of population So this is something that has been observed fairly often in these systems. Okay, now the nature of these oscillations might change. Okay, you might it might be shifted, or in some case you might have different kind of behavior, but nevertheless what I want to show through this is that this rather simple looking nonlinear differential equation can show oscillatory behavior, okay. And the reason for this oscillatory behavior is due to this critical point, okay. So if this critical point is a center, then it will show oscillatory behavior. Of course, if it becomes a spiral point, okay, so for certain choices of A and B, this can actually become a spiral point, okay. In which case what can happen is that the the species will one of the species will get might get exterminated or so on. So or actually it goes the population of the species changes, and at one point it reaches a point where the population of both the species do not change. So the rate at which the species rabbits are born is equal to the rate at which they encounter and they get killed in encounters. Similarly, the rate at which the foxes die is equal to the rate at which they are produced due to encounters. So in that case you will have both these will go to 0, okay, the rates will go to 0, okay, but their population is not 0, okay. So that would be the case of a stable spiral point, okay. I won't discuss that in detail, okay, but let me emphasize one thing, okay, that population dynamics models are often used to model chemical equations, chemical reactions, okay. And in fact one of the most celebrated chemical reaction is called the Belousov-Zhabotinsky reaction, and this is a chemical reaction that shows oscillating chemical oscillations, okay. And this is again modeled using these population dynamics models, using equations that look very much like this, okay. So this could be a concentration X, could be a concentration of one reactant, okay, and that is increases by this factor. So this is a rate of change of concentration of one reaction, okay, and it might react with some other reactant Y, okay. So it might be consumed in this way, and it might be produced due to some other process. Similarly, Y might be consumed due to one process and produced due to another, okay. And you can have the important thing is there is this nonlinear term that involves product of concentration of reactants, okay. So these kind of chemical oscillations have been observed in systems, and they can be analyzed again exactly using these population dynamics models, okay. So in this module I have tried to show you how you can use techniques of some techniques to analyze nonlinear differential equations, and this is a very powerful and very I would say it's extremely interesting because you can see by doing this analysis how you can get more information about a differential equation without actually solving it, okay. So in the last lecture of this module, I will do a few practice problems where we try to analyze nature of certain nonlinear differential equations. Thank you.